Our next keynote address is Andrew Diekman, Vice President, Marketing, Application Engineering for the Data Center Solutions Division at Microsemi, which is a wholly owned subsidiary of Microchip technology. He's responsible for product management, product marketing, product strategy, and the application engineering teams supporting Microsemi's broad portfolio of storage solutions, including SSD controllers, RAID solutions, HBAs, PCIe switches, and SAS expanders. Prior to Microsemi, Andrew was a longtime member of PMC Sierra's Enterprise Storage Division, where he helped build the business from inception to becoming the largest division at the company at PMC when it was acquired by Microsemi. Andrew earned a BS in electrical engineering from Lakehead University in Ontario, Canada. Today's talk is titled The Composable Platform Enabling Innovation Through Flexible Infrastructure. As many of you might know, one of the fastest growing segments in the data center world is composable infrastructure. And we're in for a very interesting talk on this exciting new IT architecture. Ladies and gentlemen, please welcome Andrew Diekman.
Thanks, Jay. Good morning, everyone. So I'm excited to be here talking to you today about composable and flexible infrastructure. So data centers today have the formidable task of improving operating efficiency and maximizing their IT investments in hardware infrastructure in the face of evolving and varied application requirements. Last year, data centers worldwide spent well over $140 billion on server and storage infrastructure. So what's in all of that server and storage infrastructure? Well, as we all know, there's a lot of compute, there's a lot of memory, there's a lot of storage. So let's talk for a minute about accelerators and GPUs. The data center accelerator market in 2018 was $2.8 billion, and it's expected to grow at a cumulative annual growth rate of over 50% for the next 5 years to get over $20 billion in 2023. So that is a lot of new money going into accelerators, FPGAs, GPUs, and the like. And one of the problems with those accelerator resources is that they're not being efficiently utilized. Why do we say that? Well, first, traditional architectures result in GPU I/O bandwidth being constrained, effectively starving the GPU of data required for processing. Secondly, each workload has unique optimization points for compute, for memory, for storage resources. However, typically today's data center operations are largely dealing with fixed configuration systems that cannot easily adapt to workload needs as they change. Let's talk for a moment now about memory. So over $20 billion of DRAM was purchased and deployed in data centers last year. But again, a major problem is that much of that DRAM is not being used. In many data centers, the average DRAM utilization sits around 50%. So how many billions of dollars of stranded DRAM do we have sitting in data centers around the world right now, when you think about that? This problem of stranded memory is going to become an even bigger concern in the future. As our friends at Intel were just talking about their 3D crosspoint technologies, we have emerging and precious resources like that that are increasingly being adopted and deployed. We need to make sure that we're efficiently using those resources. A second significant challenge with memory is that memory bandwidth has not been scaling with compute core counts. Core counts have been increasing, but available memory channels attached to the CPU have not been scaling at the same rate due to physical packaging and pinout constraints. The result of this is that I/O bandwidth is decreasing and memory latency is increasing on a per-core basis. So finally, let's talk a little bit about storage. We all love our SSDs here at FMS. Enterprise NVMe SSD revenue topped $15 billion last year, and that's in addition to the $10 billion or so that are being spent on spinning media and packed into data centers around the world. So what are some challenges with all this storage? Well, traditional architectures, again, require that storage be over-provisioned, resulting in stranded storage in a typical server. And even though we have very high-performance NVMe SSDs, machine learning applications require even more bandwidth than a single NVMe SSD can deliver. We also live in a world of multiple different media types and interfaces. We have SSDs, we have HDDs. In the world of an HDD, it's not just an HDD. Is it single-ported? Is it multi-ported? Is it single actuator, multi-actuator? Is it a SATA device? Is it a SAS device? In the world of SSDs, is it an NVMe interface? Is it a SAS interface? Is it a SATA interface? There's a multitude of different interfaces to deal with. Inside the SSD, the pace of innovation also continues unabated. NAND is moving from MLC to TLC to QLC. NAND layer counts are ever increasing from 96 layers to 128 to 176 layers, and latencies continue to be driven down to previously unheard of levels. New drive form factors are being designed for capacity per unit of real estate. So question, how do we avoid isolating that capacity such that workloads that don't require it are not wasting it or stranding it again due to fixed hardware configurations? So in summary, what are the takeaways here? Well, first off, we're wasting tens of billions of dollars on underutilized storage, memory, and compute resources. These resources are underutilized because they are stranded, in many cases, away from places where they could be used effectively. Storage and memory are stranded away from compute, and hardware configurations are not optimized by workload. Resources are underutilized because performance is constrained. Memory bandwidth is constrained. Storage bandwidth is constrained. Compute I/O is constrained. Secondly, the rapid pace of innovation that we see in data center technologies requires greater flexibility in the infrastructure to enable continued utility of customer platforms as hardware endpoints and as workloads and end user use cases evolve. So question, can we do better? Can we do better than we're doing now? So do we have any Shark Tank fans in the house here? So our friend here, Mr. Wonderful, Kevin O'Leary, he likes to say, stop the madness. There must be a better way. So we agree. At Microchip, we strongly believe that there is a better way. At Microchip, we believe in building flexible solution building blocks. Building blocks that can adapt to new use cases and new requirements. At Microchip, we believe in enabling system-level composability, and we are innovating to provide fabric solutions to reduce or eliminate stranded resources. With composable and flexible infrastructure, or what we like to call agile infrastructure, tremendous strides in efficiencies are possible. Enabling resource agility where physical compute, storage, and memory resources are treated as composable building blocks is the key to unlocking efficiencies and eliminating stranded or underutilized assets. Composable storage, compute, and memory enables you to optimize resources by workload and to reduce or eliminate resource stranding. We can remove bandwidth bottlenecks, removing memory bottlenecks, removing storage bottlenecks, and removing compute I/O bottlenecks. The Agile data center needs adaptable building block silicon platforms that can enable you to cost-effectively manage emerging memory and storage technologies, enabling your infrastructure use cases to continue to evolve after the hardware is built. So let's talk a little bit more in detail of how to improve GPU utilization using Microchip's Switchtec PAX Advanced Fabric Switch. This advanced fabric switch solution enables composable heterogeneous compute architectures. This includes a scalable, non-hierarchical fabric where the fabric creates virtual domains, which are dynamically reconfigurable, enabling resources to be allocated on demand, with low latency data movement as all data transfers through the fabric are managed by hardware. The nice thing about this solution, it doesn't require any special driver requirements on the host, enabling rapid time to market and reduced R&D effort for the system integrators. So let's look at how this works. It's important to realize that a Switchtec fabric is not just a collection of PCIe switches. It is a collection of fabric elements that use virtual domains to connect root complexes or CPUs to endpoints like GPUs or storage. As mentioned earlier, heterogeneous compute is becoming more prevalent in the data center. GPUs and accelerators are widely used in a variety of applications. Each application and workload may require a unique ratio of compute to accelerator resources. With native support for PCIe Gen 4 on both CPUs as well as GPUs, a PCIe Gen 4 fabric is a natural choice to allow for composable, heterogeneous compute in artificial intelligence and machine learning applications. So how do we get there? We start with a programmable, enterprise-quality, low-latency PCIe Gen 4 switch, and we add turnkey advanced fabric firmware to create a scalable and configurable low-latency PCIe Gen 4 fabric. The PCIe fabric can scale multiple switches and endpoints, and hosts are kept in separate virtual domains. In this example, we see how host 1 is assigned to 4 GPUs marked in orange, even though the 4th GPU is physically attached to a different switch within the fabric. These virtual domains are created via the flexible and configurable embedded control plane in each fabric element. The virtual domain is, in effect, a PCIe-compliant virtual switch. And here you see an example of the host in orange that has visibility to that 4th GPU. All this flexibility is enabled through firmware provided by Microchip as a turnkey solution, and the data is routed in hardware, ensuring the lowest latency. Furthermore, this architecture allows for direct peer-to-peer data movement inside the fabric. So why is peer-to-peer data movement through the PCIe fabric important or useful? Well, peer-to-peer data movement delivers increased performance and reduces latency. So in this example shown on the screen here, we can deliver 2.5 times the bandwidth by bypassing the CPU to CPU interconnect in a 2-socket system. So you can see that the GPUs in this case can deliver 26 gigabytes per second when doing a peer-to-peer transfer rather than funneling the traffic through the CPU subsystem. So a significant performance improvement here due to the direct peer-to-peer transfers. This model of composable GPUs is readily extensible to NVMe storage through the addition of NVMe SSDs into the same fabric architecture. The NVMe endpoints can simply be added to the fabric, just like a spec-compliant GPU can be, and this allows for dynamic assignment or reassignment of SSDs to different hosts as required, resulting in storage becoming a flexible and adaptable resource. So we've talked a lot about allocating entire SSDs and entire GPUs to hosts as required. What if an individual resource itself is very large? We wish to partition and share such resources. Such an example of would be a high-capacity SSD that we want to share across multiple CPUs to avoid stranding the storage. Well, SR-IOV and multi-host sharing allow for just that type of flexibility. Microchip Switchtec PCIe expanders, as well as our FlashTech NVMe SSD controllers, enable end-to-end multi-host I/O virtualization with standard off-the-shelf drivers. And SR-IOV is a reality today. There's over 8 vendors that have announced SR-IOV capable NVMe SSDs, and we have the flexible infrastructure to support this type of architecture. Notably, the applications for PCIe fabrics extend beyond the data center as well. In the autonomous car, you can have many sensors and control units that continually need to make inference decisions while driving to store data for future training. So this can be done most effectively through having, again, a low latency fabric with access to shared resources like an SR-IOV capable SSD. So we've discussed improving GPU and storage utilization and removing storage bandwidth bottlenecks with PCIe fabric solutions like the Switchtec PCIe fabric. But true agility requires composability as well as flexibility. So flexibility in the case of storage can be achieved in many different ways. Microchip believes in bringing enabling technology to market that will allow for maximum reuse, whether it be software or hardware, qualification efforts as you move from one class of storage media to another. From a protocol standpoint, our tri-mode IP and our smart storage series of storage controllers enables a platform that will allow for enterprise class, high performance, and secure NVMe storage, SAS storage, or SATA storage, or some combination of all 3 of them. From a flash media standpoint, our flash channel engines and our FlashTech NVMe SSDs provide future-proof programmable architecture with advanced LDPC ECC, including hard and soft decoding, enabling NVMe SSD firmware investments to leverage multiple generations of NAND without sacrificing quality of service. So we've addressed compute and storage composability and flexibility. What about memory? So memory innovation is happening along 2 vectors. We have near and far. So near memory innovation is about getting more bandwidth to the CPU to feed those increasing core counts within the CPU. Far memory innovation is about effectively pooling and then sharing memory, making it accessible to more machines within the rack. Microchip has been collaborating with industry partners on a number of new serial load store standards that are solving this problem, such as CXL, Gen Z, as well as OpenCAPI. Microchip at this show announced our first product in this area. It's an open memory interface to DDR4 smart memory controller. The SMC 1000 provides low latency connectivity to DDR4 via 8 lanes of 25 gig serial OMI, open memory interface, enabling the memory bandwidth required for AI and machine learning applications. This type of solution provides three primary values. The first is increased memory bandwidth. So we've reduced a 288-pin DDR4 interface down to an 84-pin OMI interface, effectively enabling a quadrupling of the memory bandwidth to the CPU. Secondly, it enables media independence. By moving the controller outside of the CPU, we have enabled the memory technology to evolve independently of the CPU. They can have different roadmaps and different cadences of those roadmaps. Thirdly, memory-intensive workloads can now be satisfied with a total lower cost of solution. DDIMMs leveraging the SMC1000 are available from some of Microchip's partners, namely Micron, Samsung, and Smart Modular. And as you can see in the image, there's a significant form factor advantage between the DDIMM and the traditional RDIMM. Microchip has a booth at the show here. I encourage you to check it out on the show floor. We have a number of really cool demos, and many of the products that I've mentioned here are demonstrated there. You'll be able to see our newly announced SMC1000 with a real workload running on DDR4 through the Smart Memory Controller. You can see a demo of our PCIe Gen 4 Smart Rock operating with our SAS4 expander, and see how our 24 gig SAS solutions combined with dynamic channel multiplexing allow you to realize the full potential of PCIe Gen 4 infrastructure, even with low speed endpoints running at 6 gig or 12 gig. Earlier in this talk, I referenced how performance gains can be realized with the Switchtec PAX Advanced Fabric. At the booth, you'll see how Microchip solution can enable improved performance by up to 7 times with direct peer-to-peer transfers. You can also see how our Switchtec PAX Advanced Fabric allows for sharing of NVMe SR-IOV-capable resources like NVMe SSDs for applications like machine learning. And finally, come and see our FlashTech high-performance flexible PCIe Gen 4 NVMe SSD controller, which enables you to future-proof for future NAND innovations while delivering best-in-class performance and innovation. So in summary, at Microchip, we believe that flexible and composable infrastructure is the future of the data center. Microchip is innovating in the areas of storage, memory, as well as compute interconnect, enabling system builders and data center operators to drive efficiencies and to adapt to evolving use cases. Thanks very much for your time today.